This is John, age 28. And this is a model of John's brain, composed of thousands of thin slices, not cut by scalpels, but by a powerful magnetic field. The technique is called Functional Magnetic Resonance Imaging, fMRI. It enables scientists to see where activity occurs in the brain. The brain is like a large network of electrical currents. These electrodes are placed in a saltwater bath. Salt water conducts an electrical current. Now the electrodes will be used to detect the currents in John's brain. About a century has passed since the first electrical brain reading, an electroencephalogram, or EEG, was scribed onto a strip of paper. Nowadays, curves from different parts of the brain are displayed on computer screens. But an EEG gives a rather unfocused picture. Using functional magnetic resonance imaging, fMRI, we get a sharper picture. Here, the optical center of John's brain is registering blinking arrows. But fMRI doesn't see the electrical currents. It sees blood flow. A neuron uses energy when it emits a discharge. The energy comes from the blood. 3 or 4 seconds after a neural discharge, there is a local increase in blood flow. This is what the fMRI detects. The brain has evolved through hundreds of millions of years, from the first bundle of nerves in primitive organisms to the nearly 80 billion neurons that our brains can now access. When we make conscious decisions, we are using a region of the brain that developed last in this evolution. This newcomer is in front, the frontal lobes. When we move, we use parts of the brain that developed earliest in this evolution. Like all vertebrates, we have a cerebellum. It controls unconscious activity, such as the muscles of our legs when we run. The brain's development is like a wave, from the oldest and most primitive cerebellum, through the occipital lobe and the temporal lobe, which we sense with, across the parietal lobe, which orients us in space, to the frontal lobes that empower us with consciousness. When we take pictures of the brain with an fMRI and EEG, we'd like to get as sharp a recording as we see here. But the two methods each have their drawbacks. fMRI gives a sharp picture of the brain, but it takes time to assemble a picture. It's like a choppy video. EEG is extremely fast, but it cannot discern well between various regions of the brain. It's like a film that's out of focus. We can achieve a better recording of what's happening in the brain by combining the two methods, but it's still imperfect. The final target for neuroscientists is the capability of registering every neural impulse in every one of the brain's over 80 billion neurons at any given time. But that's nearly infinitely out of reach, and the brain still has countless secrets.